As you settle into a comfortable position and allow your breathing to slow, let your mind drift away from the immediate concerns of the day. Imagine yourself floating in the quiet void of space, a serene observer of the cosmic dance that has been unfolding for billions of years. We are about to embark on a journey to understand one of the most significant celestial events in recorded human history. The story of Asteroid Apophis is one of gravitational forces, orbital mechanics, and cosmic chance. It is a narrative that invites contemplation on our place in the universe, a theme that can quiet the mind and soothe the spirit as we prepare to explore the science together. Let the vastness of space lull you into a state of relaxed focus, ready to absorb the wonders of our solar system. The story of Apophis begins not in ancient times, but in the very modern era of automated sky surveys. On a routine observing night in June 2004, astronomers at the Kitt Peak National Observatory in Arizona made a discovery that would send ripples through the planetary defense community. The asteroid was initially designated 2004 MN4, a mundane name following the standard protocol for newly discovered objects. As orbital calculations accumulated over the following months, a startling realization began to emerge. This was no ordinary asteroid passing harmlessly through the outer solar system. Preliminary trajectory analyses indicated a disconcertingly high probability of a future impact with our planet. The asteroid briefly reached a level for rating on the Torino Impact Hazard Scale, a classification never before assigned to any object. This event triggered a period of intense, the minus scenes activity within space agencies worldwide. The name Apophis was formally assigned later, drawing from Egyptian mythology where Apophis was the god of chaos and destruction, a serpent dwelling in eternal darkness and seeking to swallow the sun. This namesake perfectly captured the initial apprehension surrounding this celestial object, a reminder of the destructive potential that resides within our cosmic neighborhood. Physical characteristics and orbital properties. Asteroid 99942 Apophis is classified as a near-Earth object, specifically part of the Aten group of asteroids whose orbits bring them into close proximity with Earth. Current estimates, derived from radar observations and thermal modeling, suggest a diameter of approximately 340 meters. To visualize this scale, imagine an object taller than the Eiffel Tower or 3 American football fields laid end to end. This substantial size contributes to a mass estimated around 27 million tons, a figure that carries significant uncertainty due to the challenges of measuring mass remotely for a solitary object without moons. Its composition, inferred from spectroscopy's data, suggests it belongs to a class of stony asteroids known as LL chondrites. These are primitive materials, remnants from the early solar system that have undergone minimal geological processing. The orbit of Apophis is elliptical, carrying it from a point interior to Earth's orbit out to a region just beyond the orbit of Mars. This path around the Sun takes about 324 days, meaning its year is slightly shorter than our own. This orbital resonance with Earth is precisely what sets the stage for its periodic close encounters and makes its long-term trajectory a subject of such intense scrutiny. Apophis in the context of the solar system. To fully appreciate the significance of Apophis, we must locate it within the broader dynamics of our solar system. The asteroid belt between Mars and Jupiter is the primary source of most asteroids, but gravitational perturbations, primarily from Jupiter, can nudge these objects into orbits that cross the paths of the inner planets. Apophis is one such object, a migrant from the main belt that now resides on an orbit that regularly intersects Earth's. Its journey is governed by the immutable laws of gravity, a constant tug-minus war between the Sun's overwhelming pull and the more subtle influences of the planets, particularly Venus, Earth, and Mars. Every close pass by a planet acts as a gravitational slingshot, minutely altering the asteroid's path. These changes are typically small, but over centuries and millennia, they accumulate, making the long-term future of any near-Earth object inherently difficult to predict with absolute certainty. Apophis is not an isolated threat, but rather one of the most prominent examples of a vast population of near-Earth asteroids, each with its own story and its own potential for interaction with our world. The precision of the flyby. April 13, 2029 is a date etched into the calendars of astronomers and planetary scientists around the globe. On this day, Asteroid Apophis will make its closest approach to Earth, passing at a distance of approximately 31,600 kilometers from our planet's surface. To understand the remarkable nature of this proximity, we must shift our perspective to a cosmic scale. This distance is less than 1/10 the average distance to the Moon and, more strikingly, closer than the orbit of some of our most important satellites. The geostationary belt, home to communications, and where the satellites that provide critical global services, lies at an altitude of about 35,700 kilometers. Apophis will literally fly through a region of space we have heavily industrialized, passing beneath these satellites as it makes its swift traversal. For context, the International Space Station orbits at a mere 400 kilometers altitude. Apophis will pass nearly 75 times farther away than the ISS, but in the vast emptiness of the solar system, this constitutes an extraordinarily close shave, direct risks and visual spectacle. The official consensus from NASA, ISA, and all major astronomical institutions is unequivocal. There is precisely zero risk of Apophis impacting Earth in 2029. The orbital mechanics are thoroughly understood and have been verified and verified by independent teams across the world. The path is known with a precision that rules out any possibility of collision for this encounter. For the majority of the world's population, the event will be visible without the aid of a telescope. As it passes closest to Earth, Apophis will brighten significantly, appearing as a fast-moving star streaking across the night sky. Its path will be particularly visible from parts of Europe, Africa, and Asia. It will be moving at an astonishing speed, covering the width of the full moon in the sky in less than a minute. This will provide a breathtaking demonstration of orbital velocity, a visible manifestation of the laws of motion that govern our universe. For amateur and professional astronomers alike, it will be an unparalleled opportunity to observe a substantial near-Earth object at close range, an event that blends scientific wonder with public spectacle. The aftermath of the gravitational interaction. While the 2029 encounter poses no impact threat, it is far from a non-minus event in a dynamical sense. The close passage will subject Apophis to Earth's gravitational field in an extreme way. Our planet's gravity will act as a slingshot, significantly altering the asteroid's orbit around the Sun. The asteroid's orbital period will be shortened, and its path will be reshaped. This gravitational perturbation is a predictable and calculated outcome. However, the more complex and less predictable consequences lie in how the asteroid itself responds to these intense tidal forces. The side of Apophis facing Earth during its closest approach will experience a stronger gravitational pull than the side facing away. This difference, known as a tidal force, will stretch and squeeze the asteroid. For a solid, monolithic body, this might result in negligible change. But if Apophis has a different internal structure, the consequences could be profound. This gravitational interaction is not the end of the Apophis story, but potentially the beginning of a new and more uncertain chapter in its relationship with our planet. The mechanics of tidal forces. Tidal forces are a universal phenomenon, most commonly associated with the ocean tides raised on Earth by the Moon and Sun. The same physics applies when a small body, like an asteroid, passes close to a large planet. The force of gravity diminishes with distance, so the gravitational pull on the side of Apophis nearest to Earth will be measurably stronger than the pull on the far side. This creates a stretching effect across the entire structure of the asteroid. The magnitude of this tidal force depends on the masses of the two bodies, their proximity, and the size of the smaller object. For the 2029 encounter, the tidal forces will be significant enough to potentially cause physical changes to Apophis. Scientists use mathematical models to calculate the stress and strain these forces will induce. The key unknown variable is how the asteroid will internally respond to this stress, a factor determined by its internal strength and composition. This is why understanding the true nature of Apophis, whether it is a solid rock or a loose aggregate, is so critically important for predicting its behavior during and after the flyby. The YRKOV sky effect a subtle but powerful influence. Beyond the immediate and dramatic gravitational pull of Earth, a much more subtle force acts upon Apophis year in and year out, the YRKOV sky effect. This is a non-minus gravitational force that arises from the way an asteroid absorbs and radiates thermal energy from the Sun. Imagine the surface of Apophis being heated by sunlight on its day side. Hours later, as that rotated into darkness on its night side, the heated surface radiates that thermal energy back into space as infrared light. This process of emission imparts a tiny amount of thrust, akin to a very weak rocket engine. Because there is a time lag between heating and cooling, the direction of this thrust is not perfectly symmetrical. For a prograde rotator like Apophis spinning in the same direction as its orbit, this effect generally causes a slow but steady push that can widen its orbit over time. The acceleration involved is infinitesimally small, measured in nanometers per second squared, but when applied consistently over decades and centuries, it can alter an asteroid's trajectory by thousands or even millions of kilometers. The strength of the YARKOV sky effect is exquisitely sensitive to the asteroid's surface properties, its color, roughness, thermal conductivity, and density, gravitational keyholes, and long-term collision probability. The concept of a gravitational keyhole is one of the most crucial and unsettling in planetary defense. A keyhole is a tiny, narrowly defined region in space near Earth. If an asteroid passes through one of these keyholes during a close encounter, Earth's gravity will deflect its trajectory in just the right way to set it on a collision course for a specific future date. These keyholes are incredibly small, often only a few hundred meters wide, a minuscule target in the vast expanse of interplanetary space. Following its discovery, astronomers identified a keyhole associated with the 29 encounter that could have led to an impact in 2036. As more precise observations were gathered, It was definitively determined that Apophis would miss that particular keyhole. However, the gravitational landscape around Earth is complex and contains other keyholes for potential impacts in the 2040 seconds, 2050 seconds, and beyond. The primary goal of ongoing observation in future spacecraft missions is to refine our knowledge of Apophis's position and velocity with such precision that we can be certain it will miss all these potential keyholes in 2029. A miss by even a few kilometers is sufficient to ensure long-term safety, but achieving that level of forecasting certainty requires a deep understanding of all the forces acting on the asteroid, including the notoriously difficult minus-to-minus model YRKOV sky effect. The Rebel pile hypothesis. A paradigm shift in our understanding of asteroids has occurred over the past few decades. Many, if not most, small solar system bodies are now believed to be rubble piles, not solid, monolithic rocks, but loose collections of boulders, gravel, and dust, all held together by their own weak gravity and possibly very weak cohesive forces between grains. This model suggests that these asteroids are the shattered remnants of earlier, larger bodies that were destroyed in ancient collisions. Evidence for this structure comes from spacecraft visits to other asteroids like Itokawa, Ryugun, and Ben-Nung, which all revealed porous, rocky surfaces with very low overall density. If Apophis is such a rubble pile, its response to the 2029 tidal forces could be dramatic. Instead of behaving like a single solid body, it could act more like a bag of marbles being gently shaken. The stress could trigger internal shifts and surface landslides, a process scientists euphemistically call surface resurfacing event. This would not be a catastrophic disruption, but a reorganization of its surface and near-surface material, potentially exposing fresh, unweathered rock from beneath the surface. Potential surface reshaping from tidal forces. The tidal forces during the 2029 flyby could act as a geological agent on Apophis. Computer simulations that model rubble-spile asteroids under tidal stress show that material can flow, particularly from the mid- latitudes toward the equator. This could lead to changes in the asteroid's shape, perhaps making it slightly more oblate. It could also trigger avalanches on slopes, filling in small craters or creating new talus deposits. The redistribution of even a small percentage of the surface material, just 1 or 2%, could have significant consequences. This is because the YARKOV sky effect depends directly on the thermal properties of the surface. Freshly exposed rock might absorb and radiate heat differently than older, space-weathered material. A change in the distribution of fine dust, which acts as an insulator, could alter how heat propagates through the subsurface. Therefore, a physical change on the surface directly translates into a change in the non-gravitational forces acting on the asteroid, which in turn alters its long-term orbital evolution in ways that are challenging to predict with perfect accuracy. Rotational changes in their thermal consequences. Another critical factor is the asteroid's rotation. Current data suggests Apophis has a rotation period of about 30.4 hours. However, the gravitational interaction with Earth could torque the asteroid, changing its spin rate or even its spin state. If the torque is applied in a specific way, it could potentially nudge the asteroid from a simple rotation around a single axis into a more complex, tumbling motion. A tumbling asteroid presents a nightmare scenario for accurately modeling the YRKOV sky effect. For a simply rotating object, Scientists can calculate which parts of the surface are being heated by the sun and which are radiating heat at any given time. For a tumbling object, this becomes a chaotic, 3-dimensional problem. The thermal thrust would no longer be applied in a consistent direction, making the asteroid's long-term path far more uncertain. This is why pre-encounter missions, like the proposed Ramses, are so vital. They can establish the baseline rotation state before the flyby, allowing scientists to measure any changes that occur as a direct result of the Earth encounter. The OSIRIS-APX mission, a post-encounter assessment. Originally known as OSIRIS-AX, this NASA spacecraft successfully completed its primary mission by collecting a sample from asteroid Bennu and returning it to Earth. With its spacecraft and instruments still in excellent condition, NASA has extended its mission, renaming it OSIRIS-APX Origins, Spectral Interpretation, Resource Identification, and Security Apophis Explorer. Its new target is Asteroid Apophis. The plan is for OSIRIS-APX to rendezvous with Apophis shortly after its historic Earth flyby in 2029. The spacecraft will then spend the next 18 months conducting a detailed post-encounter assessment. It will map the entire surface at high resolution, looking for any changes that may have occurred due to tidal forces. Its spectrometers will analyze the surface composition, searching for any freshly exposed material. It will precisely measure the asteroid's mass and gravity field, providing crucial data about its internal structure. However, the keel imitation of OSIRIS-APX is its arrival time. By reaching Apophis after the flyby, it can only document the aftermath. It is like arriving at a crime scene after the event. You can see the evidence, but you cannot witness the event itself. This makes it difficult to definitively link observed changes to the specific mechanisms of the tidal interaction. The proposed Ramses mission, a before-during-after perspective, to address the critical gap left by OSIRIS-APX, the European Space Agency has proposed a complementary mission called Ramses Rapid Apophis Mission for Space Safety. The ambitious goal of Ramses is to launch in 2028 and arrive at Apophis in early 2029, well before the close encounter with Earth. This would allow it to fully characterize the asteroid in its pre-flyby state, measuring its shape, mass, rotation, and surface properties in exquisite detail. Then, during the flyby itself, Ramses would be positioned to observe the asteroid in real time, as it experiences the maximum tidal forces from Earth. It could witness any surface landsliding, dust ejection, or rotational changes as they happen. After the flyby, it would continue to monitor the asteroid to document the final post-encounter state. This before-during-after dataset would be scientifically invaluable, providing a complete picture of how a rubble-bile asteroid responds to a planetary close encounter. This knowledge is not just academic, it would significantly improve our ability to model the long-term orbital evolution of Apophis and other potentially hazardous asteroids. The decision on whether to fund and approve the Ramses mission will be made by ESA's Ministerial Council in late 2025, a critical juncture for planetary defense. The Global Ground-based Observation Campaign. In addition to these dedicated spacecraft missions, Apophis will be the target of the most intensive ground-based observation campaign in history. Every major optical telescope and planetary radar system on Earth that can point towards the asteroid will be tracking it in the weeks and months surrounding the flyby. Radar systems like the Goldstone Solar System radar in California and the Green Bank Telescope in West Virginia will bounce radio waves off the asteroid. By analyzing the returning signals, they can create detailed shape models and measure the rotation state with high precision. Optical telescopes will precisely track its position against the background stars, refining its orbit. Amateur astronomers worldwide will also contribute valuable observations of its brightness and path. This global effort creates a robust network of data collection. However, ground-based observations have limitations. They cannot match the resolution of a nearby spacecraft. They are subject to weather, daylight, and the rotation of the Earth, which can create gaps in coverage. Furthermore, the growing problem of radio frequency interference from satellite constellations can degrade the quality of sensitive radar observations. Despite these challenges, the coordinated global effort will provide a crucial stream of data that complements the close-up views from OS, IS-APEX and, hopefully, Ramsey, assessing our current planetary defense capabilities. The close approach of Apophis serves as a real-world test of our global planetary defense preparedness. In the last 2 decades, humanity has made significant strides in this area. NASA's Planetary Defense Coordination Office and similar entities in other countries now systematically track near-Earth objects. Catalogs of potentially hazardous asteroids are more complete than ever, though many smaller objects remain undiscovered. The Double Asteroid Redirection Test DART mission in 2022 was a historic success, demonstrating that we can intentionally change the orbit of an asteroid through kinetic impact. This proves the core technology for one potential deflection method. However, the case of Apophis highlights the gaps that remain. Our risk assessments are only as good as our physical models of these asteroids, which in turn rely on detailed data that often requires a dedicated spacecraft to obtain. While we have proven we can deflect an asteroid, moving from a technology demonstration to an operational capability for a real, large threat would require a massive, internationally coordinated effort launched with years or decades of advance warning. The 2029 encounter is a stark reminder that advance warning is a luxury we must earn through continuous vigilance and investment in observation. The United Nations framework and its practical test. Planetary defense is inherently an international endeavor. An impact threat affects the entire planet, and any deflection effort would require global cooperation. The United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, has developed a framework for international collaboration on near-Earth object threats. This includes protocols for information sharing, disaster response planning, and guidelines for the authorization of deflection missions. The Apophis flyby represents the first time this framework will be stress-tested by a real, high-profile, and well-characterized object. While there is no impact risk, the event will simulate the flow of information, the coordination of observations, and the public communication challenges that would accompany a genuine threat. It will reveal how effectively different space agencies, governments, and scientific institutions can work together under global scrutiny. Geopolitical tensions on Earth could potentially complicate the seamless data sharing and coordination that are essential for an effective planetary defense response. The 2029 event is an invaluable dress rehearsal, an opportunity to identify and fix weaknesses in our international response mechanisms before a real crisis emerges. Balancing public communication and risk management. One of the most delicate challenges surrounding Apophis is public communication. Space agencies must walk a fine line between transparency and responsibility. On one hand, they must be open about the scientific process, the remaining uncertainties, and the legitimate, albeit low probability, long-term risk. On the other hand, they have a duty to avoid causing unnecessary public harm or fueling misinformation. The language used in official statements is often carefully calibrated. Phrases like refining our understanding and reducing uncertainties are scientifically accurate, but can sometimes obscure the fact that there are fundamental physical properties of Apophis that we simply do not know and cannot know without sending a spacecraft. The media, in turn, often gravitates towards more sensationalist narratives of impending doom or, conversely, complete safety. Navigating this landscape requires a sophisticated communication strategy that educates the public about the nuanced, probabilistic nature of impact risk, while maintaining confidence in the scientific institutions tasked with protecting the planet. The Apophis flyby provides a crucial opportunity to build public trust and demonstrate the value of sober, evidence-based assessment. Apophis in historical context. While Apophis is a uniquely well-studied asteroid of substantial size, it is important to view it within the broader historical and cosmic context of impacts. Earth has been struck by asteroids and comets throughout its history, with consequences ranging from the creation of simple craters to mass extinction events, such as the Chicxulub impact that contributed to the demise of the dinosaurs 66 million years ago. On a human scale, the 1908 Tunguska event in Siberia was caused by an object much smaller than Apophis, perhaps only 40–60 meters across. Its airbats flattened over 2,000 square kilometers of forest. A similar event over a populated area today would be catastrophic. Apophis, at 340 meters, carries orders of magnitude more energy. An impact would unleash devastation on a regional or continental scale, with global climatic effects. The story of Apophis is not about a singular, unprecedented threat, but rather about our growing awareness of a perennial cosmic hazard. It is a test case for whether a technologically advanced civilization can recognize this threat and organize itself to mitigate it. The broader landscape of future asteroid threats. Apophis is just one of thousands of known near-Earth asteroids. Our sky surveys, such as the Catalina Sky Survey and Pan-STIRS, are constantly discovering new objects. The good news is that the vast majority of the very largest asteroids, those capable of causing global extinctions, have been found and their orbits calculated, showing no threat for the foreseeable future. The challenge lies with the population of smaller asteroids, those in the range of 140 meters to 1 kilometer, large enough to cause severe regional damage. Many of these remain undiscovered. Apophis belongs to this category. The focus on Apophis must not lead to complacency regarding the rest of the population. The technological and institutional capabilities we developed to handle Apophis, from precise orbit determination to deflection mission planning, must be scalable and sustainable. They need to become a permanent part of humanity's toolkit, ensuring that we are prepared not just for this one known asteroid, but for the next one that we have yet to discover. The role of science education and public awareness. Ultimately, The long-term security of our civilization against asteroid impacts depends on sustained public support and political will. This, in turn, relies on a foundation of strong science education and public awareness. The 2029 flyby of Apophis is a teachable moment of historic proportions. It is an opportunity to engage students and the public in the fields of astronomy, orbital mechanics, and planetary science. It demonstrates the practical application of physics and mathematics in assessing and mitigating a real-world natural hazard. By following the story of Apophis from its discovery and initial scare, through the refined observations that ruled out immediate impact, to the sophisticated spacecraft missions designed to study it, people can gain a deeper appreciation for the scientific process itself. It is a process built on evidence, peer review, international collaboration, and the gradual, relentless refinement of knowledge. Cultivating this understanding is perhaps our most vital planetary defense asset, ensuring that future generations continue to look up at the sky with both wonder and vigilance. A final contemplation. As we conclude our journey with the asteroid Apophis, let the steady, predictable motions of the cosmos bring a sense of calm to your mind. The planets will continue their orbits, the asteroids will follow their paths, and the universe will unfold according to its ancient laws. Our human endeavor to understand these forces is a testament to our curiosity and our desire to safeguard our future. The story of Apophis is not one of fear, but of knowledge, preparation, and international cooperation. It is a reminder that by looking outward, we learn to protect our fragile world. Now, as you drift towards sleep, carry with you the image of a peaceful, star-filled sky, a canopy of wonders that we are steadily learning to navigate. Rest well, knowing that the quiet work of discovery continues through the night.